have this online seminar. Today, I want to talk about a bit of work I've done together with Christopher Kellett. It's about two-measure formulations of input to state stability. And hopefully I will try to, hopefully I will manage to convince you that there's a bit of usefulness in there, but also that things are not so easy because some things happen that maybe you do not expect if you're introduced to the standard ISS theory for ordinary differential equations with respect to a fixed point. So, okay, great. So what will I talk about? Introduction, yes, then I will try to explain what is two-measure stability. We will talk about Lyapunov functions, conditions, and then sufficient theorems for different versions of ISS. And then the interesting part is maybe the examples that show that things fall apart, right? So that input to state stability does not imply or is not implied by integral input to state stability, and then there's still another concept that also is somehow askew to all the other properties. And our setting is the following. So we have an ordinary differential equation on an open subset of Rn. That open subset is called G. And F is, yes, nice, right? So that your favorite uniqueness and existence theorem works. And the inputs we consider are measurable, essentially bounded input functions. And in principle, in this setting, it makes sense. And we've also done a bit in that direction to consider the case that the system is not complete. But for simplicity in this talk, I would simply assume that the system is forward complete, right? So no matter which initial condition you take, no matter which input you take, the trajectory exists for all positive times. There will be a small comment later on that, but in general, that's the basic assumption. Okay, and so what is two-measure stability? Well, if I try to give you an intuition, it's an attempt of unifying various stability concepts in a common language. And there's a book out there by Lakshmikantam and Liu, Stability Analysis in Terms of Two Measures. And then there's also a famous paper, well, I think, by Andy Thiel and Laurent Prali, which gave Lyapunov theory for two-measure stability for differential inclusions. That's already in 2000. That appeared, and that has been very useful actually for our work on these problems as well. And if you're not used to measure stability, do not worry. So I just thought I'd try to see what ChatGPT will tell me if I ask it what two-measure stability is, right? So I asked today, what is two-measure stability and what is it good for? And the answer was, I'm sorry, but I'm not familiar with the term, right? And that's quite an achievement, right? To find something which ChatGPT will just tell you, I have absolutely no idea what that is, but it also tells you that this talk is about rather a niche subject, right? Okay, a niche, but I mean, there are books out there. So what's the idea? So we're interested in attractivity properties of closed sets. And for this, we will use what's the measurement functions. And so what's the measurement function? So a measurement function is just a continuous non-negative function. So you have a wide variety of measurement functions. So a function which takes values in G and maps to a non-negative number. And just to fix notation, what will be important several times will be the zero level set. So that I'll write as omega inverse of 0. So that's the set of points that are mapped to 0. Standard notation, but just so that it's fixed. Okay. And we have our system, yeah, that I described earlier. Nothing has changed with the system. X dot is equal to fxu. For the moment, I'll ignore u and we'll just look at the case of 0 inputs and define what does it mean if I'm given two measurement functions. What does it mean that the system is KL stable with respect to the two measurement functions omega-1 and omega-2? And that means that there is a KL function. I'll assume that every one of you knows what that is, with the property that, okay, so you measure the size, if you want, of the trajectory at time t, and that should be bounded by a KL function, but then here the other measurement function appears, omega-2 of x, at time t, and that should be true for all initial conditions and all positive times. Right, so we have, so if we were just to replace the measurement functions by norms, then that would be usual asymptotic stability of the 0 position of the system. And now, well, it looks a bit more funny, and it maybe is a bit more general because the omegas are just continuous non-negative functions. And so maybe let's see what can we do with that. We can define lots of things. Is it of any use? Well, to talk about this, I will need two words. The first one is, what does it mean that two measurement functions are compatible? And compatible is in a way similar to equivalence of norms, just that the equivalence is in terms of nonlinear functions, so k-infinity functions. So two measurement functions called compatible if there are two rescalings, if you want, two k-infinity functions, a lower, alpha lower and alpha upper, so that if I rescale omega-1 with alpha lower, then I'm smaller than omega-2, and if I rescale omega-1 with alpha upper, then I will be bigger than omega-2. In particular, that means that the 0 level set, which somehow is important for stability of the two functions, will be the same. Yeah, which in general, we haven't assumed anything so far about how the 0 level sets of these two functions are located. So that's compatibility, so a generalization of equivalence of norms, if you want. And then there is a class of very nice measurement functions, and these are proper indicator functions of subsets of G. And so a non-empty, well, with what I've written, it will also be closed. A closed non-empty subset of G will have a proper indicator if what? Well, if first of all, the set is precisely the 0 level set of the measurement function, but then also as you go away from the set, so either if you approach the boundary of G or if you approach infinity, the measurement functions will tend to infinity. Right, so that's the sort of properness that you want. And these are particularly nice measurement functions, but these are also the case where the theory is particularly easy. Let's put it that way. Right, so examples. So first of all, we have some stability concepts that we know, and let's see what we can do with in terms, how can we express that as two-measure stability? Well, first thing I already mentioned. So if omega-1 and omega-2 are just norms on Rn, yeah, which they could be, continuous functions, which are non-negative, then KL stability with respect to these two norms is just standard, ordinary asymptotic stability of the fixed point, which then will be located at 0. Right? So that's, in that sense, it captures that. If you are interested in compact attractors, well, then maybe take two measurement functions which are compatible, proper indicators of that compact subset. So remember, compatible means that they're equivalent in this nonlinear equivalence sense, and proper indicator means that we notice when we go to infinity in some sense. And then if you do that, then KL stability with respect to these two measurement functions will again be standard global with respect to G asymptotic stability of the attractor. Right? So very well-known concepts, maybe written down in a more complicated way. Yes, but there are other examples. For example, last week, there was a very nice talk by Jose Luis Mancilla Aguilar, who considered time-varying systems and input-to-state stability properties of such systems. And some things he said could have been said in terms of two-measure stability. Well, there was no need for him to do that, right? But it would be possible. And the standard trick is, well, if you have a time-varying system, you just introduce a new variable which takes the role of time and increase your state space, right? So instead of x dot is equal to f of t xu, we'll write x dot is equal to f of z xu, and z is a scalar variable with the property that z dot is equal to 1. So z essentially is time, right? And then if we want to say we have the trajectory which is constantly equal to 0 is a solution of your system for the 0 input, let's just assume that, and we're interested of that of stability properties of that solution for the time-varying system. Then we could look at the time-invariant system and introduce measurement functions which just have the property that the 0 level set is basically the trace of that trajectory, right? So 0 times r, if we assume that the system is defined on all of r. And that would still allow you to talk about uniform and non-uniform concepts. And if you were now to assume that actually the measurement functions omega I are just a function of x, so z does not enter into the evaluation of omega I. So basically omega I is just nu I of x for a measurement function which is just defined on G. Then if you restrict to that case, then you would talk about uniform stability concepts, uniform with respect to time for the time-varying system, right? So if we talk about two-measure stability, we essentially include large sets of discussions of what are stability properties of time-varying systems. Just note now, the unpleasant thing is that the level set, the 0 level set of the measurement functions will not be compact, right? And that is really maybe one of the points of this talk. Compactness or not compactness of these level sets is really what makes life easy or hard. Final example that would also be of interest. And there's also the concept not only of input to state stability, but also input to output stability, which was introduced by Sonntag and Wang in 2 papers, 1999 first introduction, 2000 the Lyapunov theory for that concept. And so the idea is, okay, you have your control system and you have an output, yeah, with suitable regularity and everything. And since we're not talking about input to state stability yet, but just about KL stability, ignore the input part for the moment. And then in that paper, at least 2 concepts, actually many more, are introduced, namely KL output stability, which would be in our language, just be choose omega 1. So that's the function with which you measure the evolution of the trajectory, is just the norm of the output. And omega 2 is the norm of the state. So you would compare what does the norm of the output do in comparison to the size of the initial condition. And then there's another concept which was called state-independent KL output stability. And that is just, okay, so missing something here. Anyway, so that's just, we take the same measurement functions, so they're immediately compatible in that case. And the function is just the norm of the output. So you take the norm of the output at the initial time and compare what does the norm of the solution do compared to the norm of the solution of the output of the solution at the initial point. Note again, I mean here, depending on what H looks like, but in very many cases that we would expect, again, the zero level set of these measurement functions would not be compact, which is one of the problems with iOS in any case, right? So that's where there's really some sort of non-compactness lurking there at the end. Right. Okay, so that was KL stability. And now just one thing to mention. So far, my measurement functions all had a zero level set, but there's no assumption anywhere that it does, right? So KL stability can also describe very weird things. So this differential equation, x dot is equal to 1, which is fairly boring and which is hard to imagine as saying it is stable in some sense, but it is in fact KL stable with respect to two measurement functions. And they are compatible even, and they have no zeros. So we take as measurement functions e to the minus x, and as the KL function that you need, r times e to the minus s. And if you do a small calculation, you'll find out that yes, indeed, this system is KL stable with respect to these two measurement functions given here, right? So KL stability does not mean a priori that there is somewhere in the state space a stable object. Well, that might be a drawback, but it might also be a feature, because maybe in some situations you actually want to describe that the solutions that you're interested in go to infinity, right? And that could be done in this way, right? But again, then some of the assumptions of my later theorems break down immediately. Or you intend to expand the state space and embed R into a compact space, and then maybe this makes more sense, but okay, so weird examples are possible is basically the moral, but that can be expected because just saying the measurement functions are continuous functions is so much freedom. Okay, no, this is not what I wanted. Yes. Right, so now input to state stability. Now, as everyone here hopefully knows, was introduced by Eduardo Sontag in 1989. And maybe for this, the reason I mentioned this is for this talk, the interesting thing to note is that in this paper, he immediately said, okay, oh, we could also define a different stability concept, which we'll call integral input to integral state stability. And then a few paragraphs later, it was shown that actually, yeah, we could define this new concept, but it's actually the same that we have already defined, so let's not talk about it anymore, right? And so it's a small footnote in that paper, but then afterwards, ISS is the only thing that is interesting. And integral input to integral state stability is not interesting in the finite dimensional case, at least anymore. Well, we will see here that in the two measure case, there is a distinction between the concepts, and it's maybe interesting to understand why they happen. So where are we? We have a system on an open set D, x dot equals fxu. We have a set of admissible input functions, and let's assume we are given two measurement functions, yeah, continuous and non-negative functions. And now finally we need to define what does it mean. Well, generalization from KL stability to input to state stability is then probably obvious. So we call our system input to state stable with respect to the measurement functions. If we have a KL function and a gain gamma, so that for all trajectories. Again, the thing happens if we measure the size of the trajectory with the first measurement function that is smaller than this decaying term measured in the second measurement function, but now maximum with the gain of the input. Right, so that's again a straightforward generalization. Replace measurement functions by norms, and you're back to the usual definition. And then integral input to state stability is also of interest. There, oops, sorry, how do I get back? Yeah. There's the only thing that's happened. So we rescale the omega-1 here with a k-infinity function on the left. And on the right, we have the maximum of this decaying terms in terms of the omega-2 measurement of the initial condition, and then the maximum and, well, a rescaled size of the input. I forgot the norm here. That is, yeah, so it should be gamma of the norm of u of tau here. Right, and we know in the standard case for a fixed point in ordinary differential equation, there's a strict hierarchy, so ISS implies integral ISS, but not the other way around. And maybe I should mention last week's talk again, right? Because there it was already seen that in the time varying case, this relation between ISS and integral ISS already breaks up, right? So if you haven't seen it, go back to last week and look at that talk, very interesting. And so I will also tell you that this is the case in the two-measure case. And then now you can say, oh, we already know that, right? Because last week's talk is covered in the two-measured case. And so the example was already shown there. Yes, true. But maybe the point here is that what we want to stress is maybe that really the point is not the time varying nature so much maybe, but the non-compactness of the attractor that we're really dealing with. Well, that's philosophy maybe. And then we need integral input to integral state stability, so IISS with respect to our two measurement functions. And basically what we do now is the measurement of the size of the trajectory is also in terms of an integration along the trajectory of the measurement of the trajectory. And that should be now smaller than something which depends on the size of the initial condition as measured with omega-2, and the integral of the input, again with a norm missing here. Okay, so we have these three concepts. And now we want to talk about Lyapunov theory for these concepts. And in Lyapunov theory, you're probably familiar that it is very useful to have radial unboundedness of some sort of the Lyapunov functions. And radial unboundedness usually is defined in terms of the norms that you're looking at for measuring the size of your trajectory or your initial state. Well, in our case, that doesn't really make much sense because we have no norms. Oh, well, norms exist, of course, but we are not interested in norms. We are interested in our measurement function. So the replacement of radial unboundedness is this property here. So we have then omega-1, omega-2 unboundedness, if you want, because it's not really radial in any sense. But concept is the same. So we want to have k-infinity functions so that alpha-1 omega-1 is less than what should be eventually a Lyapunov function, and alpha-2 omega-2 is larger. Yeah, so same idea, but we have to adapt to our formulation of what are stability properties, what do they look like. And then we can define what does it mean. We have an implication form to measure ISS Lyapunov function. Yeah, so that's smooth. Yeah, because we want to differentiate, and then the non-smooth case is not, that's not the important issue here. So I'll just assume everything is smooth. It's an omega-1, omega-2 unbounded function in the sense we've just discussed, such that we have the usual implication, just that looks a bit different. Well, it actually looks the same. So if v of x is bigger than chi, then gradient v times f should be, so there should be a decay in v. And so the relation to the to-measure case is really hidden in this omega-1, omega-2 unboundedness, right? So that is where we see, what does decay in V mean? Well, that has a relation to the measurement functions, not to norms or anything. And then, of course, we also want to have Lyapunov functions for the other stability concepts. So for integral input to state stability, an integral input to state stability Lyapunov function is, again, omega-1, omega-2 unbounded. We need that all the time. And then the condition is in dissipation form now. Again, gradient v times f. This looks very familiar, should be less than minus rho v of x plus sigma of u. And sigma is class k, that k here is wrong. And in the integral input to integral state, we actually want here, the difference is that here we want the rho in k infinity, and here the rho is just positive definite, right? So actually this is a stronger condition than the following one. So that gives you one relation at least between integral input to state stability and the IISS condition. But for this, we need to have positive theorems now. And okay, so first theorem is for ISS. Yeah, so if we have an implication form, so that was our first definition, to measure ISS Lyapunov function, then the system is ISS with respect to these two measurement functions. And of course, we are always interested in converse theorems as well. The converse situation is not that easy. And so what we could do was assume compatibility of the measurement functions. Yeah, so we need to basically assume that we can replace one measurement function by a rescaled version of the other one. Then it is possible to show that ISS with respect to omega-1 and omega-2 implies the existence of an implication form to measure ISS Lyapunov function. And in particular, in that converse direction, that's the point where the theory developed by Thiel and Prali becomes essential, right? So the main step is, the proof is very similar to the classical case, and the main step is to playing that back to the existence of robust feedbacks, and for that, then a Lyapunov function, a robust Lyapunov function exists, and the existence of that robust Lyapunov function is guaranteed by Thiel and Prali, the paper that I mentioned earlier, right? But to make the changes work, we need that compatibility along the way. And now let's look at integral input to state stability. So if we have dissipative form to measure integral input to state stability for our given measurement functions, then the system will be integral input to state stable. The converse is also true. We believe, we just haven't written it up properly yet. Something that needs to be done. And there's a small remark here. I assumed I have this, I mentioned that I have this blanket assumption that I assume that the system is forward complete. Actually, at this stage, that blanket assumption is not really needed. In the sense that if omega-1 is a proper indicator for some compact non-empty set, then it essentially follows from the properties of the Lyapunov function, the unboundedness that is in the proper indicator property, together with the decay estimates that you get from integral to input to state stability, that the system has to be forward complete, right? So I had this blanket assumption. At this stage, there's a point where I do not really need it. But anyway, that's hurt. And the same thing is true for integral input to integral state stability. So again, if we have a dissipative form to measure IISS Lyapunov function, then the system is integral input to integral state stable. And the same remark about completeness holds as before. So nothing happened. So, but okay, and here probably is the part where the converse theorem is really wide open. There the question is, what is the correct formulation of the Lyapunov function to get one? That is, yeah, there's still problems here. And now I want to show you some examples that where these three concepts, ISS, integral ISS, and integral I, integral SS, where these concepts fall apart. And for this, it will be useful to understand a bit what properties destroy KL stability. And basically, the intuition is, well, KL, if you're just thinking of an ordinary fixed point, then maybe the intuition is, well, if the fixed point is not stable and you're in finite dimensions, there is a trajectory which emanates from that fixed point and forward in time goes away from that fixed point, right? And so, yeah, we want to copy something like this. And for this, I recall the definition of alpha limit sets. So alpha limit sets are like omega limit sets, just in the other direction, negative time. So alpha of x, what's that? That's the point in Rn with the property that we have a sequence in G, a sequence of tk's that go to infinity, such that the sequence yk converges to y, and x, that's our x here, is always the solution that if I start in yk, this is all for zero input, if I start in yk and go tk time step forward, then I end up in x. I mean, another way of saying this is, if I am in x, the solution actually exists backward in time until tk and is then at yk. Right. Okay, so that's the alpha limit set. I mean, that's standard. That's just for the sake of completeness. And so, lemma. Assume we have a zero level set of omega-1, which is not empty, and which is a closed subset of Rn. Yeah, that's not entirely obvious. So there's a sort of assumption here, because a priori omega-1 is just defined on G, and G is an open set. So the zero level set in omega-1 is, of course, closed in G, but that does not imply closed in Rn, right? But for this thing, we want closed in Rn. So basically, we're staying away from the boundary of G with the zero level set. And now, if there's a point in G where omega-1 is positive, and the alpha limit set of that point has non-empty intersection with the zero level set of omega-1, then doesn't matter which other measurement function you take. You can pick any omega-2 that you like. It won't help you. The system has no chance of being zero input omega-1, omega-2 KL stable. And from the definitions, maybe you noticed, I should have pointed that out maybe, omega-1, omega-2 ISS implies KL stability for zero inputs. Yeah, because you just have the maximum term there with the norm of the input, but if that is zero, that goes away, and then you end up with KL stability. Same with integral input to state stability, right? So not omega-1, omega-2 KL stable implies not ISS, not integral ISS. And then this is the funny thing. To conclude that the system is not integral input, integral state ISS, we need that omega-1 and omega-2 are compatible. Yeah, so this lemma does not include that the system is not KL stable, but still integral input, integral state stable. And that can indeed happen, right? And that's the point of the example. So very simple example. So we are one-dimensional. So x dot is equal to fx times u squared plus 1. Yeah, so the control input just can speed up the direction in which you're going, but doesn't do anything else. And this f doesn't really matter. The picture is more important. We have two fixed points for the system, one at 0 and one at 1. And the evolution is from the left, I converge towards 0. Here in the middle, I run away from 1 and converge towards 1. And from the right, I converge towards 1. Yeah, it doesn't have to be that function. Could be any function that creates this phase portrait if you want. Okay, that's a fairly simple system. So let's look at a nice measurement function for this. And what we'll do is we'll take a proper indicator of our fixed point, right? And so that would be 1. So omega-1 of x is x squared times x minus 1 squared, right? So the zero level sets is precisely these 2 points, 0 and 1. And of course, if I start at 1/2, right? So the trajectory converges in this way. That means backwards in time, I converge towards 1. So the alpha limit set of 1/2 is just the point 1. And that's contained in the zero level set of our measurement functions, omega-1. But that's precisely the condition of our lemma, right? So the lemma says, no matter which measurement function omega-2 we pick, the system is not KL stable with respect to these two measurement functions. And it's neither ISS nor integral ISS. Yeah, so that's nice. But then the lemma also says, well, if I want to conclude the same thing for integral input, integral state stability, I have to assume that omega-1 and omega-2 are compatible. So let's take an omega-2 that is not compatible. Yeah, and so what we'll do is we'll take the Lyapunov function equal to omega-2 is equal to x squared. And then you have the small computation. And from this decay condition, actually, you will see that you get the integral input to integral state stability property. So that function is neat in that sense that it's not the zero level set of our system with respect to that measurement function is not KL stable. The system is not input to state stable, not integral input to state stable, but it is, if you take a nice measurement functions like x squared, which is not compatible with omega 1, it will be integral input to integral state stable. And the reason for that is basically, well, there's this point here where the trajectory doesn't behave in the right way in terms of the measurement function omega 2, yeah, because basically here we don't move. But in omega 1, this is 0, right? So the inequality that you need has omega 1 on the left-hand side, that should be small, and omega 2 on the right-hand side, that should be large. And then the convergence that happens towards our 0 level sets of omega 1 is what guarantees that system is still integral input to integral state stable. So second example, here we have a two-dimensional system now with x1 and x2 as the components, and it's defined on all of R2. So yes, x1 dot is an independent dynamic. This is not influenced by x2. It's just x1 times absolute value of u times 1 minus phi of u. And x2 dot has this nice ISS part, minus x2 plus u. And then here a coupling where x1 and x2 play a role. And all of these is modulated by these functions eta and phi. And what are they? So they're smooth functions taking value in 0, 1. And they basically tell you something about where is it actually possible to influence using these functions. So phi vanishes outside of this compact interval. So if phi vanishes, then here we just have x1 times u. And phi reaches a supremum 1 at u is equal to 2. And then this will just make x1 dot equal to 0 if that happens. And eta vanishes where x2 is large and does nothing or is equal to 1 if x2 is small, relatively small, smaller than 2. And I have to tell you, of course, what are the measurement functions that we're looking at for this system. And the measurement function are the following. So we'll just take omega 1 equal to omega 2 is just the absolute value of x2, right? So x1 does not play a role in terms of the measurement functions. And the 0 level set of these omegas then is, of course, unbound, right? Because x1 can be as large as you want. Omega 1 or omega 2 will simply not notice that. Right. And then the question is, okay, stable in any sense. And it's a bit of calculation, which I won't show here, but it's a bit tedious. But you can show several things. So the system is not integral input to state stable. And basically, this term here is responsible for that. Of course, then there also does not exist a corresponding Lyapunov function in dissipation form. And in fact, there's, if you look for any dissipation formulation Lyapunov function for the system, you will fail, right? So no reasonable dissipation formulation Lyapunov function exists that will give you some sort of decay for the measurement functions, right? So integral input to state stability fails, integral input to integral state stability fails, but we have this nice dissipation Lyapunov function. So that's again a short calculation, which I will not show, but you take a very easy function, 1/2 x2 squared, and then it's easy to figure out what should be the gain of u, and that will be an implication form ISS Lyapunov function. So the system is in fact ISS, yeah, with respect to this chosen measurement function. So omega 1, omega 2 ISS to be precise. The system is not integral input to integral state stable. it's not input to integral state stable. And so we really, if we now take the first example again, where somehow the opposite occurred, we see that a lot of things that we are used to in this context fall apart. And the problem here is really the non-compactness of the level sets. So as long as you have compact level sets, as long as you have proper indicators for your measurement functions, the theory works just as you're used to, right? The formulas look a bit differently, but they are essentially the same. So conclusions, well, so two-measurement stability is nice because you can formulate many different things in terms of measurement functions, but just by choosing the right measurement functions. What I have not mentioned, maybe should have also mentioned, is that also if you're interested in incremental stability, there is a two-measurement stability formulation of that. Then the nice or simple part of the theory is that if you have compact attractors with compatible measurement functions, and that are also then on top of that proper indicator of your compact attractor, then yeah, there are things to do, but not much exciting happens. You basically you are in smooth waters, and everything that you have to do has been done before in other contexts. And in the non-compact case, things become a bit more complicated because standard implications simply are no longer true. And you have to be a bit more careful in finding the right argument. And in particular, then for converse theorems, the approaches that we're maybe used to do not work as smoothly as one would hope, and there's a bit more work to be done. Okay, so that concludes the talk. Thanks very much for your attention, and maybe at this stage there will be some questions.